Okay, so for this class, yeah, it's a sponsored class, and yeah, it's sponsored by Gertrude. So I hope you guys will appreciate and say hi to her when you see her. Yeah, it was bought for the mind guys, but I'm sure everyone will appreciate it. Okay, so let's begin. You guys requested that we look at 15 through to 17, so we're going to go through those. We might not do all the questions here, but we'll pick the best of the bunch. So let's see how it goes. Question 15 is probably one of the straightforward ones here. The only thing that you have to understand is the interpretation here. So what are they saying in the question? The question is saying for each of the following rods lying on the x-axis. Okay, so for each of the following rods lying on the x-axis with varying density, so they're saying that this expression is for density, find the moment about the origin and the center of mass. So this moment is to be evaluated about the origin, and they also want us to find the center of mass of each one of those. So how does it go? So first thing that you have to understand is that these expressions which are being presented here, they are not functions of like the way these down here are presented, or like the way these are presented. The expressions in question 14 are actually describing the density. So here the density is varying. What does that imply? It actually implies that these rods will have a fixed. Let's try to just picture them. So you can look at the rods to say that. Okay, so like they're kind of linear. By linear I mean you have something like this, and then you have something like that. Then you have something like this, and then like that. So they're uniform. Let me say that they're uniform, but of course they're saying that their densities are varying. So the key thing is when we're performing our integral, density will not be a constant. Density is going to be affected. That's where we're starting from. And the other thing that you have to get here is just recall the formulas. Just know the formulas to use here. Once you know to say density is going to be integrated over, it won't be constant in this case. The next thing you need to get are the formulas that you're going to use in this case. What are we using? So in this case, what we're going to have, you just have to remember three formulas. Basically, it's two, but you can split them into three. So if you wanted to find, let's say, the center of mass. So, well, they want us to get what? Was that find the moment about the origin and the center of mass. Okay, so how do we do that? So if we wanted to get, let's say, the center of mass, of course, the center of mass will have two coordinates, x and y. Okay, so the center of mass will have two coordinates, x and y. So let's say these would describe the coordinates of the center of mass. How do we get these parameters? So this is where it all starts. Basically, if we wanted to get the x coordinate of the center of mass, we can easily multiply the moment for that particular part. So this is going to be the moment about the origin divided by the mass of the object. And in this case, if we say that this is lying on the x-axis, if we say that this is lying on the x-axis, which I think is what the problem is saying, so these are lying along the x-axis. So if they're lying along the x-axis, we can see that in this case, the y-coordinate of the center of mass will have to be 0 since these are literally on the x-axis. So the y-coordinate of the center of mass will already have to be 0. So all we have to determine is where is what is the x-coordinate of the center of mass. So our focus will be this expression. So for this expression, we see that to get the x-coordinate of the center of mass, we just need to find the moment about the origin and the mass there, m. So here, the expression for the mass, for the moment about the origin, so this is going to be the integral from a to b. And since these are all about the x-axis, so a to b can be seen as the length from where you're starting from to where you're ending. Okay, still having a lot of people joining us. Okay, so in this case, we're going to have the expression that perhaps you have to remember here. X, of course, being the length, and then the expression for the density, and then multiplying dx. So this is the expression that you have to keep in mind. Now, what if they said these? This is if the rods are lying on the x-axis. Yeah, you have to know how this can change. If the rods were lying on the y-axis, you should be flexible enough to see that this expression would change to become a to b, and then this would have to be presented as y. The density now would have to be a function of y, and this is going to be with respect to y. That is if the rods are lying on the y-axis. In this case, they're lying on the x-axis, so we're going with this expression. Just thought I'd put it out there, because once you memorize one expression, you might easily fail to adjust. Okay, so this expression will give us the moment about the x-axis, about the origin I mean, and the next thing that you need to get is the expression that gives you the mass. And for the mass of the shape, you're just going to integrate from a to b again, but now you won't have this distance, the expression for the distance. Here you're just going to have the density, a function of x, multiplying dx. So this is what you're going to integrate to get the mass. Now, where do these expressions actually come from? How did we arrive at these expressions? If you want to know that, of course, from as you're preparing for the test, you might not really need to know where they're coming from, but I think it gives you a bit of more confidence when you understand where these expressions are coming from. And perhaps one thing you just have to get is they all come from the expression for density. And you know the expression for density. Mass, volume, density, you know to say that's going to be mass over volume. This is what usually gives you the density. But here, depending on what you have, under centroids also in CEE, you're going to have an area density. Okay, so as I was pointing out here, this is the mass volume density. But in this topic, sometimes you might be given an area density depending on what you're trying to achieve. Okay, so if you're going for an area density, of course, this can be expressed as mass over the area in question. So that is if you're going for the area density. And in this case, to get the mass, this can be written as mass is equals to density multiplying the area. Now, depending on what you have, what you're working with, if it's an area density or if you're looking at a length density, of course, that is going to be mass over the length you're dealing with. Then, of course, this would be mass is equals to the density times the length. Now, if you wanted to get the moment about a point, you know to say, if you're getting the moment about a point, you need to know what that point is, and then get the distance from that point to wherever you are, somewhere there. Now, generally, this is where the whole thing comes up. When you look at this expression, it has a part for the distance. So x there is basically representing the distance in question. And this part here is just giving us the mass. So here we're getting the moment due to a mass. So this density times dx, this is basically just trying to give us the mass part. So you can look at it as density times the length there. But the length expressed as a differential length since this is going to be changing. So this was just an over-the-head description of where the formula there is coming from. But a more descriptive approach, I think, is what we'll look at when we start describing centroids in CEE. I think that one is more straightforward on what you need. But here, our focus would be on how you use these two expressions to get the coordinates of the center of mass. So that is where our focus is going to be. Let's take the first question, for example. In the first question, what are they saying? They're saying the density has the form 1 minus x over 2, and this is changing from 0 all the way up to 2. So they want us to get the moment about the origin. Other than the moment about the origin, they also want us to get to find the center of mass. The moment about the origin is one of the steps we need when trying to get the center of mass. So for this expression, we'll directly start by going for the moment about the origin. So we're not set to get the moment about the origin, we're getting the integral a to b x density and then dx. So when you're integrating with respect to x, a and b will be values of x. When you're integrating with respect to y, if this was y here, then a and b would have to be values of y. In this case, this is with respect to x, so a is the smallest value of x, while b is the maximum value of x. From here, our density, of course, takes this form, 1 minus x over 2. The smallest value of x is defined as 0, and the maximum is defined as 2. So from here, we see that it's now just basic integration. You can distribute the x there, dx. So again, this is basic integration. We can distribute the integral so that we look at it as from 0 to 2, x dx minus from 0 to 2, x squared over 2 dx. So the first one will be x squared over 2, changing from 0 to 2. So if I leave you at any point here, don't hesitate to ask, don't hesitate to just, you can text with your question or you can go right ahead and just talk to me. So the second part here, to integrate this, I already have that 1 over 2, which is already present. I'll integrate the x squared, I'll add 1 to the 2 to make it 3. So this will be x to the power 3 over that same 3. This is changing from 0 to 2. Simplifying this, upper limit first, this will be 2 to the power 2 over 2. Lower limit to make that a 0, so I won't go through that. Then next we have 1 over 2. Upper limit first, 2 to the power 3 over 3. Lower limit will be 0, so I'll skip it. So we have 4 over 2, which is just 2. Then next we have 1 over 2. And then this is going to be 8 over 3. 2 goes into 8 4 times. We now have 2. We now have 2 minus 4 over 3. So this expression is giving us the moment about the origin. We can combine these, of course. This is going to be 6 minus 4 over 3. And this is going to be 2 over 3. And whatever the units. So this ends up giving us the moment about the origin. And once we're done with moment about the origin, we can go ahead and now get the mass. So to get the mass, we're seeing that we're now just integrating the density with respect to x. And our density was that expression. So I'll just get this. But now it's just the density, so that x which was there doesn't have to be there. So now for the mass, again, as I was saying, this is not there, just the density here is what we're integrating. So we can distribute 0 to 2. I can just go right ahead and integrate. So the integral of dx will just be x minus, here we're going to have 1 over 2. Let's say from 0 to 2. Here, I'll say x squared. Then this is going to be over 2 there. From 0 to 2. So I just integrated that the way it is. That would be x. Then here it goes to x squared. And the 2 shows up down there. Okay, so now we simplify. Plug in the upper limit. That will just be 2. Lower limit will be 0 minus. This will now be 1 over 4. Plug in the upper limit. That will be 2 squared. So that will be 4. 4 and 4 will cancel here. So I'm going through this the simplification relatively fast. So if I make a small error, don't hesitate to point it out. Okay, so 4 and 4 will cancel there. So that now this is just 2 minus 1. And this will end up being a 1, whatever the unit. Okay, so after getting the mass, we needed the mass so that we can obtain the x-coordinate of the center of mass, because this was just the moment about the origin divided by the mass. But we saw to say that the moment about the origin came out as, so the moment about the origin came out as 2 over 3. So that comes here, 2 over 3, and then the mass came out as 1. So when you divide, of course, this will remain as just 2 over 3. And then, of course, whatever the unit. So to present it now, the center of mass. So the center of mass, remember, it's x bar, comma y bar. But since this lies on the x-axis, this will be equal to, the x-coordinate will be 2 over 3. The y-coordinate will be 0, since it lies on the x-axis. So this is going to be the coordinate of the center of mass. Earlier we found the moment about the origin. So to answer James' question there, so like I was saying, the question we're just from working out is for a rod lying on the x-axis. And for that one, we saw to say that the x bar will be equal to the moment about the origin over the mass. And for this one, since it lies on the x-axis, the coordinates ended up just being this, whatever this will give us, comma 0. Where the moment about the origin ended up being equal to from A to B, and then we had x, the density a function of x, dx. This was for a rod lying on the x-axis. If our rod was now lying on the y-axis, how would it change? Well, for starters, if it was lying on the y-axis, now it's basically something like this. Okay, not that. Go back. So if it was lying on the y-axis, what would now happen is, it's like our rod will now be somewhere here. Implying that, okay, that's too small. Let me modify that. So like our rod will now be somewhere here. Meaning that if we wanted to get the x-coordinate of its center, not that the x-coordinate would have to be literally along this y-axis, implying that the x-coordinate will now be the one which is equals to 0. It's the y-coordinate which will be changing. So meaning this one will actually have a form x bar, which is 0, comma y bar. So this is how the coordinate of the center of mass would be. And to get y bar now, this is the one that will be equals to the moment about the origin over the mass. And in this case, the moment about the origin would be an integral from A to B. Now it will be y. Why am I saying y? The distance you'll be using will be a vertical distance. So it will be y multiplying the density. Even the density, because this lies on the vertical axis, even the density will be a function of y. And this will be integrated with respect to y. So basically, this is how we would approach it in this case. The mass, of course, would have to be the integral from A to B, the function of y with respect to y. A and B will be functions of y. So even the range that you'll be given maybe something from 0, less or equals to y, less or equals to some number, maybe let me say n. Have I answered that, James?
Yes, sir.
Okay.
Yes, sir.
Okay, so yeah, basically this is how it goes. And yeah, I saw a comment again. There was someone who was asking to say that, is it possible to have one which lies both in the x and both in the y? Yes, it is possible. I think in this tutorial sheet, I haven't seen one. In CEE, you will encounter those. I think we'll describe them as we go through centroids in CEE. That is going to be the center of mass of a line or of a wire. We're going to describe all those in CEE. Any other questions? I think there was a question, there was a hand up from Chaku as well. Okay, I'm guessing that has been answered as well. Okay, so it's the same approach for B here. Okay, yes, the class is being recorded. So it's the same approach for B there. The difference is just the density is different and the range is different. Same approach. But perhaps I should comment on C here. Looks interesting. So C, notice that we've been given the density as a composite function. Why not say a composite function? It's in two parts. And here we have from 0 less or equals to x less than 1. And then next we have 1 less or equals to x less or equals less than 2. So this is what we have here. How do we approach it in this case? So here again, because the format is similar to what we did in the previous question, I think I just want to show you the treatment of those two functions. And then after that, you should be able to work it out. Okay, so because the density takes different shapes for different intervals, here, same thing, lies on the x-axis. So basically just trying to find x bar, m0 over m. So m still takes the same shape, the integral from a to b, x, and then you have the density, a function of x, dx. But because the density takes different shapes, you have to define it for each particular interval. What am I saying? It's like you are splitting the interval into two parts, A to B, then to C. So from A to B, the density is defined by this. From B to C, the density is now defined by this. But added, this is what will give you the full thing. What am I saying? You first have to move the smallest value, that's from 0 to 1. In that interval, the density is defined by 2 minus x dx. Now you need to combine plus. In the second part, what is happening? The second part starts from 1 and it goes up to 2. So the second part is now from 1 to 2. And in that interval, the density is just x. So this is the only thing that changes here. This is how you're going to get the moment about the origin. So just integrate these two functions and then add your results. In the same way, to get the mass, something similar. The mass will be different for each interval. From 0 to 1, the mass will be given by 2 minus x dx. But from 1 to 2, the mass will be given by x dx. And when you integrate this, add the results. So this expression will give you the mass. This expression will give you the moment about the origin. So basically, this is how you're going to treat this. I'm sure at this point, it's just integration and simplifying. Once you get the two expressions, you can get x bar by just saying m0 over m. And whatever the value you're going to get, that will be x bar, comma 0 to give you the center of mass. Do we have anyone with a challenge here? I've just explained how you'd get it and the interpretation of this presentation of the density. Yeah, are we okay with this, or do we have a question? Or maybe Lloyd, you have a hand up?
Yes, sir.
Go ahead.
I'm quite blank on the part of the interval. Looking at this wise function, we're having 1, like 0 is less than or equal to x less than 1. I'm seeing that 1 is not included, but we are using it as our upper bound. So how are you going to explain on that point? I think that's what I'm behind. How are we including 1 and 2 in our bounds when in actual sense they are showing that they're not included in the domain?
Okay. So I get your point. Now, one question that I'll just give you there is, let's see, where is it not included? Okay, so let's take this one. So here 1 is not included in the upper boundary there. So that's from 0 to 1. But if you're not going to put 1 here, then what are you going to put there? That'll be the question that you'd have to answer. The thing is, because these are real numbers, you can't say that because 1 is not there, I'll pick the nearest to 1. There are so many, it'll be difficult for you to pick the nearest to 1. So here you have to go up to 1. Even if you don't say that 1 would be included, you have to go up to 1. I don't know if that gets it. We look at these expressions, even in, I think, is it CEE, they get to appear so much, and this is how we usually treat them. We have to go up to 1, even if 1 is not included in the domain. We have to get as close as possible to it. All right, so we're moving on to question 16. How do we work out question 16? So in this case, they're saying find the center of mass of a centroid of a thin plate covering the region described below. So that thin plate looks like we're going for the center of mass of an area, since that is a thin plate. Okay, and then the regions are bounded. So for question A, they're saying that these are bounded by y is equals to x minus x squared. And then we have the other boundary there. We have y is equals to minus x. And the density here is described as that. So here what you see is that the density is actually constant. So seeing that the density is constant, this expression actually simplifies a lot. So with the density constant, it now implies that the density expression, even when you look at the expressions we're using here, we had density here, we had density there. So now density will not be affected by the integral. So meaning that it's just going to skip out. But here, of course, we're not looking at the center of mass of a line. Here we're looking at the center of mass of an area, of a thin plate. So how do we approach it in this case? So for these expressions, the first thing that you might want to do is, if it is possible, try to create a picture of what is actually happening there. So I'll go straight first to the picture. So try to create a sketch of the problem. And the sketch, you don't have to be super accurate with it. All you need is to understand the type of graphs you expect from the functions that they have presented. Okay, so we have two functions. One is a straight line with a negative gradient. So meaning that that one goes like this. The other one is a curve. Seeing that the x squared term has a negative coefficient, it means that this has a maximum turning point. So we expect this one to curve in downwards. So here first, I'm just placing them here. I don't really know where they're passing and so on. So we're just placing them there. Next up, the intercept. I want to just understand where they're intercepting here. So when I look at the function, the quadratic there, I have y is equals to x minus x squared. I can easily just get x here. I want to get the intercept here. 1 minus x. This is equals to 0. So it intersects the x-axis at x is equals to 0. And when 1 minus x is equals to 0. So meaning x will be equals to 1. So I know it cuts the x-axis here, and that x is equals to 1. So I'll remove this and I'll draw it better. So it cuts the x-axis at 1, at 0 I mean, and let's say at 1 somewhere, something like this. Let me adjust. Then I'll change this so that they get to intersect something within my graph. Okay, so we have something like this. So in this case, this is the shape that is being enclosed. And what we want is to find the center of mass of this area. Where is it going to be? And how do we find the center of mass of such a shape? So to do that, what we're going to do is we're going to first, let's understand the formulas we're going to use. Here, we're going to go directly to get the center of mass, the x coordinate. Here, we're going to have both coordinates, the x and the y. So the x coordinate here is going to be obtained by integrating. Since this is an area, so this is going to be an area integral. And then this is going to be, so when you're getting, so understand how the formulas work here. When you're getting the x coordinate, the distance you're going to use here is going to be the x coordinate of a centroid, a differential centroid that you pick. I'll describe what that is in a minute. And then so the x tilde here, it's actually the x coordinate of the centroid for the differential section you have selected. So the distance from here up to where its centroid is going to be, that is the one that we're taking as x tilde. And then you have to multiply this with, since this is a differential, we're going for the differential, an area, so this is going to be multiplying dA, and then over, so the key thing is just this x tilde, what it is, then over the integral of the dA. So this formula is going to give you the x coordinate of the centroid or the center of mass, and then y tilde, not y tilde, y bar will be the integral. This is going to be y tilde and then dA. So again, y tilde will be the y coordinate of that centroid. So this centroid here is going to have an x tilde, comma y tilde. So now we just have to see how to find those two. This is going to be over the integral of dA. So dA will be the same here, 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 and there. So we'll see exactly how to get it in a minute. All right, so yeah. To evaluate this, the tricky part here is knowing how to choose your x tilde and your dA. So that is where the trick is going to be. So let's say I wanted to find the x coordinate of this area here. So let's start with that one. So to get the x coordinate, like I pointed out, the first thing you want to understand is what is going to be the x tilde. We have already selected our differential section, and this is going to be a vertical bar. So when you're going for the vertical bar here, or the vertical rectangle there, first thing, the thickness of the rectangle. So I'm going to isolate it. I'll bring it this side. The thickness of this bar, notice that this thickness is in terms of the x-axis. It's in the horizontal axis, so you can get that as a dx. So the thickness is a thickness in the x-axis. Had we gone for a horizontal bar, notice that in this case, the thickness would have been in terms of the y-axis. So this would have been a dy. So that would have been a dy there. Okay, but let's focus on the vertical one with the dx there. And how about the vertical axis? Well, in this case, when you look at the vertical axis, or the length of this bar, the upper part of this bar is controlled by that curve. Remember what that curve is? That curve is the quadratic. So let's label it as y1. The lower one is the straight line. Let's label it as y2. So the upper part is the quadratic, y1. The lower one is the straight line. We labeled it as y2. So to get the length L here, just from y2 up to y1, so the length can be seen as the upper y1 minus the lower y2. So that if we wanted to get the area of this differential section, since it is a differential area, so go with dA, this will be equal to, you have to multiply the length, and remember the length is controlled by these two, y1 minus y2, multiplying the thickness. The thickness is dx. So this is how we're going to get the area. So now we know the shape of dA. This is going to go there, and it is also going to come here. How about x tilde? So for x tilde here, just understand how this is going to go. Since you're dealing with dx here, x tilde just has to be exactly right on the middle of this section. And when you draw that line coming up to the central point of this section, notice that here, when you move this vertically along this section you have selected, that x will remain the same. Based on that, we can easily just get it exactly the way it is. As an x, it won't be changing there. Okay, so I hope you have got how x is being selected there. Have you got how x is being selected? If we're going for x, notice that x can be picked up just the way it is, straight away from there. If you are going for y would have been complicated, because y, you don't really know exactly where the center in terms of the vertical axis is. So for y, you'd have to get the upper, add it with the lower, and then half them. That will tell you exactly where the middle of this rectangular bar is. Add the uppermost, the lower, and with the lowermost, and then divide them by 2. That will tell you exactly where the center in the y-axis is. But in the x-axis, you can just define the x position. I rotated it. You just define the x position as just an x. Since the distance from here up to there, it will be the same throughout. What am I saying there? X tilde will just be x. But dA is going to be y1. What was our y1? The upper function. Y1 was x minus x squared. Then minus y2. Y2, the lower function. The lower function we went with minus x. Because that is minus x, this just ends up being positive x. And then dx here. So this is over dA. dA again is just that expression. So that is just this part here. So x and x will give us 2x minus x squared dx. Mapalo, you have a hand up?
Yes, sir.
Go ahead.
Can we have a situation whereby the x tilde is given in form of a certain function?
X tilde given in form of a certain function. I think wait for when you look at y tilde, because y tilde will be seen as we'll see how y tilde will be equals to y1, which is basically that function minus x, and then it will be plus the second function, that x minus x squared, and then divided by 2. I don't know if this qualifies to say given by in form of another function.
Alright, sir, thank you.
Okay, so here's where we are. So we have simplified. Let's just simplify this a little bit, because we also have to define the boundaries. Here it's just, I can keep this as a for now, but we have to define what the boundaries of integrations will be. So we have x here. Inside there we have x plus x, that's 2x minus x squared dx over 2x minus x squared dx. Now what are our limits of integration? Because we're integrating with respect to x, both in the numerator and denominator, our boundaries of integration also have to be values of x, the minimum most to the maximum most. The smallest value of x, we see that is just a 0 there. So the smallest value of x is going to be 0. How about the maximum value of x? Since we're going for just this area bounded by the two functions, the smallest has to be here, the maximum has to be here. So what is the value of x at that point? So we see that that's the point when the curve is equal to the straight line. The curve is x minus x squared. At what point will this be equals to minus x? That is what we are trying to get there. So I just have to solve for x here. I get x minus x squared. This becomes plus on the left side equals to 0. When is this equals to 0? These two add up to give us 2x minus x squared. When is this equal to 0? X comes out. 2 minus x. When is this equals to 0? We see that this will be equals to 0 if x is equals to 0 or if 2 minus x is equals to 0. What does this mean? It means that we have two values of x when x is that, or when x is equals to 2. So this is the second value of x that we are looking for, and that occurs at that point. So the maximum value of x will be at 2. So this is what we have. Now we can easily move towards integration. Okay, so what do we have there? X bar is now equal to, numerator, distribute the x. You just say this is 0 to 2. This is now 2x squared minus x to the power 3 over. This is 0 to 2, 2x minus x squared dx dx. Let's integrate now. 2 plus 1, 3. So this is going to be 2 over 3x to the power 3. Minus, next one, x to the power 3, that will now be 4. So x to the power 4 over 4. So I'm going through this very fast. If I make a mistake, please don't hesitate. In the denominator, we have here, it will be 1 plus 1, 2 divides to cancel this, so it will just be x to the power 2 minus. This will now be x to the power 3 over 3. 0 to 2. When you substitute 2 in the numerator, that will be 2 over 3, and this will be 2 to the power 3 minus 2 to the power 4 over 4. In the denominator, we have 2 to the power 2 minus 2 to the power 3 over 3. Now it's just simplification. I think this is pretty straightforward. That is 8, 8 and 2, that is 16 over 3. Minus, that is 2 to the power 4. 2 to the power 4, this is just going to be 16 over 4. And then this is going to be 4 minus 8 over 3. Okay, so we have found the x coordinate of our centroid. Now we're trying to get the y coordinate. It's a similar approach. The y coordinate is the area integral y tilde and then dA over the integral of dA. dA will be the same as before since I'll stick to the vertical section I selected, so dA will take the same shape, but that will be different. It's now just this part here. But you have to see that because I'm saying dA will be the same, it will mean that in the denominator, I did integrate in the denominator previously. Previously, I had the integral of this, that was dA. Simplified, it came to this. Then it came to this, it came to this. Simplified to this. Eventually, it was 4 over 3. So I won't go through all that trouble unnecessarily. I know the denominator will reduce to 4 over 3. So now I just want to focus on the numerator. And the only thing I have to get now is y tilde. And remember, for the vertical section, picking exactly where the centroid of that differential section is going to be will be a little bit tricky. It's not like for the x tilde where we just went to say, okay, this is going to be our x. For us to pick that as our x, it must be constant throughout, because that will be the midpoint throughout our selected section. But we see that for the vertical section, that is not true. It's going to be different. Is it up to here? Is it up to there? Is it up to there? There is that question mark. Based on that, to understand exactly where the centroid or the center for this section is going to be, we're just going to use the functions given. The highest point of our function is controlled by the function labeled as y1. The lowest is controlled by the function labeled as y2 when we were doing this. So to find exactly the midpoint of this function, we're just going to say the highest point plus the lowest point, then half them. This would tell us exactly where the midpoint is. So that is what we're going to utilize. So this is how the formulas that you have, I think from a mathematical point of view, you have f of x plus g of x divided by 2 in one of the functions. So here I went with y1 plus y2 divided by 2. Then this gets to multiply dA. And for dA, we already saw what dA was. So when we're getting x bar, we got the expression for dA as it's simplified to this. This was our dA. So just get this and we'll bring it here as our dA. Okay, so with that done, what is our y? Our y1. So if we recall, our y1 is x minus x squared plus our y2. Our y2 is negative x. And then this remains 2x minus x squared. Is it 2x? Yes, reduced to 2x. Dx there, divided by the integral of dA. Again, it just reduced to 3 over 4. So the limits, because this is still in terms of x, so this will still be from 0 to 2. So we're still going from 0 to 2 since this is integrated with respect to x. When I simplify this, I will have x minus x. That will be 0. So this will remain as just minus x squared here, multiplying 2x minus x squared dx. And then this is over 4 by 3. We continue simplifying. The minus x squared multiplies in. This becomes minus, that won't show up. Okay, so this will be the integral from 0 to 2. The x squared will become the positive one, so it will be x to the power 4. And then the 2x will now be the negative one as it becomes x to the power 3 dx over 4 over 3. Instead of keeping on writing 4 over 3, I'll just take it up. I know when I take it up, it becomes, that was 4 over 3, it becomes 3 over 4 when I take it up. Okay, so next up, 3 over 4. I hope you guys followed how this ended up being this. If you haven't, you can quickly just say so that I explain through.
I just explain that.
Okay. So basically, what happened there? Harvey, you have a question? So I'll distribute.
Yes, sir.
Go ahead.
Yes, that you're supposed to ask it. I don't see the option.
You don't see the what?
The half.
The half.
Negative x squared over 2.
Ooh, yes. Thank you for that. Thank you for that. Here, this was f1 plus f2. We said this is supposed to be halved. Yes, thank you for that. Yeah, this is supposed to have over 2 here. Yeah, we literally left it out. We would have gone too far. Thank you for that, for spotting that. Yeah, so basically it's what we wrote. Where did we write it? Here, yes. The top part is what becomes x minus 2x, not x minus 2x, x minus x squared. This is f1, then plus f2 is minus x. But then we said we have to divide it by 2. So this is what we forgot earlier. Okay, now we can do it the right way. We can proceed. So that over 2 is there. Let's just bring it back. Let's change all this. Just the 2 which is there. Everything is still the same. Have a question? So what I'll do is I'll just quickly bring out that half outside. So this is now 1 over 2 here in the numerator there. So that this will still be x minus x, which will be 0. And then this will still be minus x squared. The only thing left there, then 2x minus x squared. The denominator is still 4 over 3. So again, for this one, it will just have this half outside here. The minus x squared multiplies in, then divided by 4 over 3. Okay, then from here, when this division changes to multiplication, we know to say these will swap. The 4 over 3 will swap to become 3 over 4. So that now when we multiply, it will, being a constant, it will multiply down. The 3 will multiply the 1 there, becoming 3. 4 will multiply 2, becoming 8. So this is from 0 to 2. So they'll not be affected. Left at the dx, there's a dx here. They'll not be affected by the integral, so that will still remain. So here I have x to the power 4 minus 2x to the power 3 dx. So now we can integrate. 3 over 8. When we integrate, x goes to the power 5 over 5 minus, this is now 2x to the power 4 over 4. So we have integrated, this is from 0 to 2. 2 will cancel once there. So now 3 over 8. X to the power 5 over 5. X to the power 4 over 2 from 0 to 2. Now I can plug in the upper because when you put the lower, it will just be 0. So the upper, this is now x, that's, we're putting 2 there. 2 to the power 5 minus 2 to the power 4 over 2. So now we have 3 over 8. And then 2 to the power 5, that is 32. And then this will just remain 2 to the power 3, which is 8. So it reduces to this. And then now we have, we can simplify this however it works. This will be 32 minus 5 and that will be 40 over 5. And then finally 3 over 8. This reduces, the difference there will be minus 8 over 5. And then 8 and 8 cancels there. So that now we have minus 3 over 5, whatever the units. So we have y bar, we have x bar. So the center of mass for that shape, the x bar, we got 1. Y bar, we have minus 3 over 5. Does it make sense that it is negative? Let's quickly go to our shape and try to analyze it. From a quick glance on our diagram, have I gone too far up? Yes. Quick glance on our diagram, you should see that even if you tried to find exactly where the turning point at the topmost point is, if you try to find where it is, you quickly see that majority or a majority of the graph is actually down here, implying that it only makes sense that the center of mass is down here. In the y-axis, it has to be negative. So just by quick analysis, you can anticipate that the y-coordinate of the center of mass will have to be on the negative side. The x-coordinate, however, it makes sense that it has to be positive because this graph is all this side. So it's all on the positive side. So we anticipate that the x-coordinate will have to be a positive value. And this is how our answer comes out like this. Okay, so any questions here?